Following on from the calculation we performed in the previous video and the activity that we conducted in class, I want to just reiterate the way that we can simplify the binding energy calculations. And that's just by considering the energy that would be released for one atomic mass unit. So what we're going to do here is consider energy from one atomic mass unit, and basically that just means the conversions that we're going to perform in order to get from atomic mass units to mega electron volts. So the first thing that we'd do in that calculation would be to convert from one atomic mass unit to kilograms. So that means that we'd have 1 multiplied by the conversion factor, which is 1.661 by 10 to the negative 27 kilograms. So that converts the mass into kilograms. We then need to multiply that by the speed of light squared, so 3.00 by 10 to the 8, and that's going to be squared. We then divide that by the conversion factor to get to electron volts, so 1.60 by 10 to the negative 19, and finally we'd then also need to divide that by 10 to the 6 to get the answer in mega electron volts. Now if you go through and use those values, it won't quite come out to this value I'm about to write, but if you use the extended values or the unrounded values for the speed of light, the conversion from atomic mass units to kilograms and from electron volts to joules to electron volts, the value that you would get there is 931.5 mega electron volts. So one atomic mass unit is equivalent to 931.5 mega electron volts. Now that's a conversion that's stated in the data booklet. It's in the one of the tables with constants. They include, so basically that's sort of looking at what one atomic mass unit is in energy. They have that written slightly differently as electron volts per speed of light squared. So that basically means that they're sort of still multiplying by the speed of light so that these are both in units of mass. So you can think of this unit of electron volt per speed of light squared as being a unit of mass. But I'm just going to leave it at that conversion there. That speed of light squared aspect is not particularly all that important. The last thing, just to again reiterate, is the binding energy per nucleon. So we saw that for the larger nuclei the binding energy increases, but in order to determine where the most stable isotopes are, we need to look at the binding energy per nucleon graph, as shown here. And a few things to note, as is indicated on the graph, the peak of that graph, so where we have the maximum binding energy per nucleon, the peak of the graph is around, so it's in the vicinity of iron and nickel. So they're the ones that have the highest binding energy per nucleon. The second thing then is that the stable nuclei, so keep in mind that when we're talking stable nuclei, we're talking from the very large to the very small. The stable nuclei tend to be at the top of the region that you can see on that graph. So what I mean by that is that if you imagine a line across the top here, that's where the stable nuclei tend to be. Anything below that would be tend to be a little bit more unstable. And the last thing there is that when an isotope decays, what it basically means is that it's going to move further up on that graph. So when an isotope decays, the daughter nucleus has a higher binding energy per nucleon. so that means it becomes more stable. It doesn't necessarily mean it has become stable, just means that it's more stable, and if we, as we saw, we usually have a chain of decays that would occur from an unstable nucleus, and so let's say we had an unstable nucleus here. As it goes through that chain of decay, it's sort of gradually going to move up and to the left, particularly if it's alpha decay, but ultimately the end product will be somewhere close to the top of that region there that we can see. If we're looking at some of these smaller nuclei, it's not quite as clear-cut, given that there are quite a lot in here that are stable. So the stability of the smaller nuclei is a little bit harder to determine, given that the strong nuclear force and the electrostatic propulsion behave slightly differently because the nucleus is so small. So when we're talking about these points, we're usually talking about the larger nuclei over here, rather than the smaller ones in here, where there are quite a few that are stable. Generally speaking, anything that's small, as we saw, would decay by beta decay, so that means that they're usually going to be moving up in that graph, given that the nucleon number won't change, but the binding energy per nucleus will, per nucleon, will increase.